The purpose of this lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly, straight down. I dropped an object, constructed a computational model to calculate the position of the cup with both the effect of gravity and the effect of gravity and drag. My results showed that both of my models overpredicted the position of the cup during almost the entire time interval. My models of gravity and drag were almost identical until time equaled about 0.3 seconds. Then the plot of gravity and drag was greater than that of gravity alone. Here's a photo of my system. I chose to drop a blue solo cup from eye level. I dropped it upside down to fulfill the falling somewhat slowly requirement of the lab. I oriented my system in the following way. The bottom of the cup is the origin. Towards the floor is then the negative y direction. The initial velocity of the cup is 0 in the x, y, and z axes. I began my tracker analysis as soon as my hands were off the cup. This way, all of the analysis was of a free-falling object. During my tracker analysis, my video became blurred as the object dropped, so I chose the middle of the blur as my point mass for my tracker analysis. The time interval for the tracker analysis was 0 to 0.567 seconds. Finally, I prepared my calibration stick to be the height of the solo cup, 0.121 meters. To construct the first model of gravity alone, the net force for Newton's second law was only the effect of gravity. This was simple. F net equals the mass of the ball in meters times negative 9.8, the quantity of the acceleration of gravity in meters per second. This is negative because I chose the y-axis upwards to be positive. To formulate the next model of gravity and drag, I included in my net force the force of gravity from the previous example, but also added a force due to drag. Lab instructions indicated to model the effect of drag by a force whose direction is opposite to the direction of motion, and whose magnitude is proportional to the square of the object's speed. To get this relation into code, I used the mag function, which takes the magnitude of whatever you put in parentheses, in this case, a vector. In this model, I also added the drag force with a yellow arrow. With both of these net forces, I formulated the Python module to repeat Newton's second law from 0 to 0.567 seconds. Since there is no way to calculate the b value, the proportionality constant, I plugged in values around 0.017 until my final position from the Python module equaled my final position in tracker. I had to do these steps for both modules. As you can see, the experiment position is nicely parabolic, something to expect from a free-falling object. This is because the force of gravity interacting with the cup is accelerating the cup downwards at a rate of 9.8 meters per second. Therefore, the slope of the experiment position versus time is getting more and more negative, and therefore is parabolic. As you can see, there's some discrepancies between my two models and my experiment position. I believe that the difference between both model plot and the experiment plot is due to my human error in the tracker point mass plotting. Both models, in comparison with the experiment, show that the cup is lower than it should be, defining what it should be as the model of the effects of gravity and drag, what happens in real life. If I had chosen a point mass in each frame slightly higher than I did, then the tracker's outputted y values would be slightly greater than they are now. This would result in less discrepancy between the experiment and model plots. Let's briefly compare the two model plots. The model of gravity's effects has a final position greater than the effects of gravity and drag. This is because, with a drag force in the opposite direction of motion, the net force is greater in the opposite direction. This results in a smaller magnitude of acceleration in that direction. Over a distance, this equates to less distance traveled. The comparison of these two plots is just what we expected. Finally, for the two lab questions. For the what does it mean question, none of the models predict a terminal velocity on such a short time interval. This is because that there is no chance for the force of drag to equal the force of weight. If it did, the graph would become linear at that point. The position at this point could then be used to calculate the terminal velocity of the cup. To address the what-if question, which was that if the object was thrown downward, how would the terminal velocity compare with just dropping the object alone? The answer is that the terminal velocity would be the same for both cases. Because it's the same object with the same mass, it will also have the same qualities of resistance. Thus, the terminal velocity would be the same, no matter the circumstances. This concludes my lab presentation.